Well, hello, YouTubers, and particularly Year 12 Methods students. We are looking at Academy V presenting mathematics video today on inverses of square root functions. Like, subscribe, and share if you find this useful. Okay, so here's a challenging question more at the end of, like, parts F or something of the question. And so you have a square root function, and it tells you that D is the maximal domain. And I'm not going to assume you know how to do that because it's A, helpful to know, and B, it'll help you graph it as well. And it's all about graphing. So with maximal domain of a square root function, anytime you have a square root, whatever's inside the square root must always be positive or 0. So in this case, what's inside there is 2x plus c, and that will tell us our maximal domain. And if we take away c from both sides, we get 2x is greater than negative c. And then if you divide by 2, you get x is greater than or equal to negative c on 2. So I'm hoping that it's not too much of a stretch of imagination to know that it is a square root shape starting at negative c on 2 and with a y value of negative 1. Okay, and we're gonna leave that there for now and just look at the questions. So you have part 1 saying for what values of c does g of x equal the g inverse have no real solutions? And part 2 is asking you almost the same thing, but they're asking you for exactly one real solution. So what you actually have going on is this particular graph hitting the inverse, but we also know that the inverse is going to cross the original graph at a y equals x line. Now I probably need to draw that in over here. So here's my y equals x line. And I'm going to put in my y-axis and x-axis. I like red, so let's do that. And here it is in its basic form. So we've got our x line, x-axis, y-axis, and the y equals x line in our line of symmetry. So we are looking for no real solutions. So basically, if I pick this up, it has to either, well, it actually can't be out here because even though my graph doesn't extend that far, it's actually going to cross the y equals x line at one point. At that particular point there'll be two real solutions. And again, it stays having two real solutions until we hit this point here, which I haven't drawn very well. Basically, there'll be a point where you only have one real solution, and then you have no real solutions after that. And I'm deliberately picking up the graph and translating it across because all that changes is the c value, which is where it sits, where it starts on the x values. So if I draw that out in slow-mo, here's my graph. It has two real solutions if it crosses twice, and one real solution if it crosses just the once. And no real solutions if it never touches at all. So down here, perhaps. That doesn't look very good, so let's try that way. Not much better. There we go, that's slightly better. So no real solutions. So this corresponds to using your discriminant. So the hard way, which I don't recommend, is to go through the work of finding the inverse function and then making them equal each other. Bad news. The easy way is to just say that the original function equals the G inverse if the original function equals y equals x. And then you solve for that. So if I take my original function and write it out, g of x equals that, square root of 2x plus c minus 1, I believe, just checking that. Yep. And we make it equal x. These two equal each other, basically. So we have 2x plus c in a square root bracket minus 1 equals x. And then from here, it becomes a quadratic, which you must use the discriminant for. So this is the short overview. Expand this equation to get a quadratic. Apply the discriminant to find either 2, 1, or 0 real solutions. Okay, so we are going to do that. If you have 2 real solutions, that means the discriminant, which is b squared minus ac, minus 4ac, is positive. If you have 1 real solution, the discriminant is 0. And if you have no real solutions, the discriminant is negative. Okay, so I'm going to first get the equation to a quadratic form, then we'll find the discriminant. So my first step is to undo the subtraction by 1. So we get square root of 2x plus c equals x plus 1. Then I want to get rid of this square root, so I must square both sides. So I get 2x plus c equals x plus 1 squared. And then from here, I want to get a quadratic, so I need to expand the right-hand side. And a lot of people will do x squared plus 1 and forget all about the middle term. So I'm putting in a little highlighter so you remember that the middle term is twice of 1 times x. And then we got 2x plus c on the left as it was. If we now subtract 2x from both sides, they disappear. And if we subtract c from both sides, you now get 0 equals x squared plus 1 minus little c. That is our quadratic. A is 1, B is 0, and C is 1 minus C. So our discriminant is b squared minus 4ac. I should probably put that up here. Let's do that. And so our discriminant is 0 squared minus 4 times 1 times 1 minus c. And for reference, I'm going to highlight all the A's with one color. That's from the 1 in front of the x squared. And I'll highlight all the B's in one color, so that you can actually see the B's. And I'll highlight all the C's in one color. So this is capital C in my discriminant. Okay, so this gives me 0 squared is 0. Take away 4 times 1 times 1, which is minus 4. And 4 times 1 times negative c is positive, so I have plus 4c. So we flick back to the original question. We wanted no real solutions. So no real solutions means that the discriminant is less than 0. So we take our negative 4 plus 4c, make it less than 0. And so if we solve for c, we would get 4c less than 4, divide by 4, c is less than 1. And that is sufficient for our answer. If we now look at part 2, I'm going to just pick that up and start that again. For part 2, it's asking you for exactly one real solution. And part of the answer comes from taking the same approach as part 1, which is to use a discriminant. And this time you want the discriminant to equal 0. So that's great. We can take this part here, which is our discriminant, make it equal 0. It's pretty good. It's equal 0, which means that 4c equals 4, divide by 4, you get c equals 1. However, when you look at the answers have one other bit. And so if we look back at our slider, which I had graphed up here, I'm just going to pick that up again. Mental slider, I mean. What you have is a y equals x line like so. And the graph has a little bit of information that you may or may not notice. If you factorize it out, this actually has a shape where it's not a one-to-one gradient like so, like it would be if that was a 1. If that's a 1, then it's a, for example, if you start at 0, 0, not that it does, it would go to 1, 1 next. But because you've got a 2 in there, that changes the gradient. So here's a little bit of a recap. If I've got the square root of x, it's going through 1, 1 right there. And if I put a little 2 in there with the x, what's happened to it is it's going to go through 2, 2. Very interesting. And so if I was to go to square root of x minus 1, it moves everything across, but it has the same shape. And if we put the 2 out front there, what that means is, if you look closely, if I take one step to the right, 2 steps to the right, actually, it'll be 2, 2. That's probably the best way of thinking about it. So what that means is, instead of being a 1-to-1 like so, it's going to be a 2-to-2 like so. Obviously, these might be different, but the difference is from here to here, a change of 2. How is that helpful to us? Well, it just helps us to slightly adjust the shape. Does that help us? I think so. So if I pick this up again very carefully, just the graph itself, if c equals 1, then negative c on 2 is equal to negative a half. And so your starting point is negative a half, negative 1. And so if I graph that on here, I need a grid. Let me turn on the grid. Grids over there. Maybe I need a bigger grid. Okay. So if I graph this, I'll have the axes again. Pick them up. only without the other bits. Oh, that's not a bad result. And it will start at -1, sorry, -1/2 and -1. So if I have a 1-to-1 scale, then this is my starting point. And I'm pretty sure that will mean it will cross at 0, 0. How do I know that? If y equals 0, then we have 1 equals all of that square root. Let's just test that. And that's what you're saying, isn't it? C is 1. Yep. And so if y equals 0, then 0 equals all this minus 1. So that means 1 equals all that. And that means if you square both sides, you get 2 bracket x plus 1/2 equaling all that. Oh, maybe it doesn't. And then you get 1/2 equals x plus 1/2. And yes, x equals 0. So that means it will cross over at the origin as well. So the shape is going to be from here to here, and it's going to look something like that. Now, knowing what I know about the scale, it's going to actually hit at this point here. All right. How is that relevant? Well, if I put in the y equals x line, which is at a 45-degree angle, then that means that the graph of the square root function only hits the y equals x line at one point. Excellent. However, the discriminant doesn't actually tell you about the other cases where you have this square root that has slid over to your left. In other words, c is a larger number. So in my mind, I am picking up the square root shape, which is this, and I'm sliding it to the left. And once it gets past a certain point, it is only going to cross that line at one point. Now, it's easier to see this with a calculator. So I'm going to pull up my Desmos and put in a C slider. And I'll put in the actual graph, 2x plus c minus 1. Add a slider for c. And you can see that c equals 1 corresponds to having the origin or the intercepts coincide. If I go to the right and make c larger, you can see that it does find, you do find there is a point where here it has two solutions. So, and it's just above 2. If I go down 1 in the slider, two appears to be the point where you have two real solutions. And then between 2 and 1, you've got two real solutions. And then as it is less than 1, you have no solutions. All right. So the question is still, we want exactly one real solution. And so one case is when c equals 1. And the other case is when c is, what was it? Less or more than 2. was when C was greater than 2. And to confirm that, the point where you have two real solutions, and the very last one at that is when this point and this point both lie on the y equals x line. And because you know that has a y value of -1, if it lies on the y equals x line, your x value must also be -1. And so to find that borderline situation, x is -1 and y equals -1. So if we go back to this equation here, because assuming we didn't know what c was, you would plug in x equals 1, sorry, -1 and y equals -1 as well. So y equals -1, x equals -1 goes in here, and y equals -1 goes in there, and then we can find out what c is. Now, -1 equals -1, so they equal 0. You square both sides, you still get a 0. And so then if you divide everything by 2, that gives you 0 equals -1 plus c on 2, and you get 1 equals c on 2. And then if you multiply by 2, we get c equals 2. So c equals 2 is the case where there's two real solutions, and it's the borderline. If you move to the left, as in c is bigger, then you're only going to get one solution. It's going to go something like this. I hope that helps, folks. Like, subscribe, and share, and good luck. Thank you very much.